I have been working on pavement instrumentation and pavement monitoring systems. So my paper over here is for the condition assessment using sensing technologies, and so I'm a part of European Training Network, SMARTY, and this is the project. This is under the project of wireless box road monitoring system. And so basically a little bit introduction about pavement instrumentation and a little bit what we are doing. So we are having a pavement analysis using different sensors, and the idea is to have characterization of the pavement properties and have a behavior testing of pavement. So there are two types of pavement analysis which are usually done. First is the destructive analysis, which is a sample of pavement is taken to the laboratory and some tests are run over that. But we are working on the non-destructive methods where different instruments and sensing sensors and these technologies are used for in order to get the pavement analysis and pavement properties. So we are working on pavement instrumentation, which includes different kinds of tools and different kinds of sensors which are embedded in the pavements, and for the structural assessment and behavior analysis. So the ultimate or the main objective is to have the evaluation of the performance of the asphalt concrete, and for that we have been using different sensors and different technologies for this specific objective. So basically we are measuring the deflections for the pavement. So during a passage of load, there is the induced deflection basin, which is induced in the different layers of the pavement. Here we have defined one of the example of the pavement model, and there are different layers of the pavement, and whenever there is a passage of load, some vertical displacement occur during the passage of the load. So this is basically what we are focusing on right now. So for that we have different sensors which can actually measure the vertical displacement within these layers of the soil. And these, so basically this deflection is important because it will ultimately give us the modulus of the pavement layers, which will define us how it is deformed or how it has changed during the periods of time and during the period of different temperatures. So as for measuring the deflections, there are two types of methods. So the traditional methods are to go on the site and have the measurements taken, which is using the falling weight deflectometer or Benkelman beam. So these devices are very labor intensive and they are expensive, and they need to be done like once or twice a year. So they're not very continuous, and they don't give us continuously information about the pavement. So what we are working on the remote measurements, where we can have sensors embedded in the pavement, which is connected to a data acquisition system, and which will give us information continuously without the intervention of, or without the need of being on the site to get these measurements. So here is the whole approach of what we are going for. So what we want is different sensors to be embedded on the roadside, which are going to be attached to a wireless board, which will do the configurations and data collection and everything. And once we have this instrumentation part, this can direct it to the road asset manager wirelessly, without having to be stayed in on the site to get these measurements. And then the data is available to the road asset manager for the analysis and behavior testing. So this is the whole approach that we are going for. And in the paper, this is the first part what we are working on, just the description of the first part that we are working. So we are working on different types of geophones, which will give us the vertical displacement information. What ultimately geophones gives us, that it gives us the information about the vertical velocity within these layers. So we convert these vertical velocity information into the vertical displacement, and also gives us the information about the different vehicle types and also the vehicle speeds. So that's the information that we get from these geophones. And also they are very sensitive, so the typical measurement in the deflection measurement in the pavements is between 0.1 to 1 millimeter. So it's pretty accurately measured the values. So this is why we are choosing these sensors and these geophones, and they are relatively small, so they can be easily embedded in the pavements. Initially, so the first part is to test these sensors, or to see whether we can use these sensors in the test site or not. So first we are trying to model the pavement, what type of deflection values we can get. So we are using a software to model the deflection values, and then we are going to test these sensors in a laboratory setting to see what kind of results we get from these sensors. So first, the modeling part, which is done through a software called Alize. It's used for the elastic pavement models, and so we have modeled pavement deflections using this software, but this software can be also used for stress and for measuring the stress and strains within the specific load vehicle types. So here we can see this is the pavement model, which we are using, and this is the representation of the deflection that we expect from the pavement. So this defines the 5-axle load. As we can see, this is very important for us, because this actually defines the vehicle type that we are going to use, or that can actually give us information of the vehicle type. So the signal, each peak of the signal represents the 5 axles of the vehicle. So this is a very important information that we get from these displacement values. So the test we performed was on the vibrating table. So this vibrating table is attached to a controller and amplifier. So we excite different kinds of information, or different kinds of frequencies, and that are given to these vibrating tables, and and all these sensors are attached to this vibrating table, and this will give us this will measure the vibrations within the required parameters, and then it will give us the ultimate responses. So the reference here is used, the laser displacement sensor, which is used as a reference. As it is a laser sensor, it cannot be used within the pavement. So we are just using this as a reference, as it's giving us very accurate results for the vertical displacement. So this laser sensor is used as a reference, and all the other geophone results are compared to these reference. So different test settings were done. So a sinusoidal wave, which is the pulse signal, was used and was inputted in the vibrating table at different amplitudes and at different frequencies. And also the truck signal, which is which represents the truck solicitation. So that is also applied at different amplitudes and at different speeds. So the measurements that we got was actually, they had a lot of complications. So first was these sensors had some kind of, these sensors were giving us vertical velocity. So we wanted vertical displacements, so we had to change or convert these values into velocities. And also they had some level of noises which were not easily removed by just converting these values. So what we did, we different kinds of signal processing techniques in order to improve these signals and make it more accurate to the reference signal that we got. So just to give an overview or just an overview about the signal processing that we did. So this is the signal which has without any integration, or this is just the vertical velocity of the geophone, and that is the simple integration that we did with the displacement values that we got. But the results had these upward lifts, which were not very related to what we did. So what we did is we applied a high pass filter and we removed the noises which were apparently just in the lower frequencies, and then we amplified the signal and we applied the integration, and then we applied the Hilbert transform. The Hilbert transform was a very key point for us because it removed what it did is the 90-degree shift of the signal, and we removed the upper part of the signal, or it shifted the upper part of the signal in the lower parts, and this is ultimately we got the result which was very, very close to what we got in the which was very close to the reference signal. So here the reference signal, as it is the laser signal, without any processing, the signal was very different from the reference signal. And then when we applied the processes, the signal was very close to what we wanted to achieve. So the results here, which I'm going to show, is with regard to the pulse or the sinusoidal waves, and also the truck signals that corresponds to the truck solicitation. And same kind of treatments are applied to both these signals, and same kind of the settings of the laboratory tests were also the same. So these signals represent the pulse or the sinusoidal wave. What we saw in these results is that at very lower amplitudes, the signal had significant amount of noises. And even after the filtering, we can see the noise in the signals because the amplitude was very, very less. But when the amplitude was increased, the signal had very less noise, and also the filtering worked very, very well with the higher amplitudes of the signal. Same kind of trend is also received or we observed in the speed of when the speed is high, the noise signal is also higher, but at higher amplitudes, the speed is higher, but still the signal processing pretty much worked with the higher amplitudes. That phone GS11 had slightly better results than the other. It's not very, very different because we can see from here these results are pretty much the same, but with GS11D has some little better results from the other one. So the treatments for these results were pretty much the same, just there was a difference of the cutoff frequencies, where we kept the cutoff frequencies for higher frequencies were higher, and the cutoff frequencies for the lower speeds were very low, and also the amplification depended on the speed of the signal or speed of the vehicles. So this is the first stage of. So next steps are we have already done the test tracks and we have used geophones as well as accelerometers, and these are not part of this study, but we have already done some tests with accelerometers and other types of sensors, and they pretty much work very well with the pavement monitoring systems. And we have, so the next step is that we can have the real test site, and we can have these sensors embedded on a real test or on a real road and see how these perform, because we don't have controlled environment over there. We don't know the load, we don't know do not know the parameters, and this is why it is important to see how it behaves in a real test site. So this is the next objective of our study. So that's it. Thank you so much. And we have a conference which is X-rated pavement testing, and it's going to be very interesting because we have speakers from UC Davis and Nottingham and University of Granada. So if you are interested in pavement testings, and so you can have a look at these, and that's it. Thank you.
Thank you very much.